Hello. In this module, we're going to discuss sedimentation, which is one of the water treatment processes that can be done in household treatment or also at the community scale, as discussed in our previous modules. Sedimentation by itself is not a complete water treatment, but it can be a necessary preliminary step to be followed by filtration and disinfection before safe storage in the case of household water treatment. To discuss sedimentation, we'll introduce the concept of turbidity. We'll define turbidity, and we'll show how turbidity can be reduced either through simple settling using gravity or by enhanced settling through the addition of chemicals called coagulants. Turbidity is simply the presence of suspended particles in water. If the particles are large, they can eventually settle out of water through gravity. But if they're very small, they will remain suspended. They won't settle. Particles can be made of organic materials, such as microorganisms or algae, or they can be inorganic, made of silt, clay, or other minerals. There are a variety of units used to measure turbidity. Nephelometric turbidity units are based on scattering of light through turbid water, while formazan turbidity units are made with reference to a standard series of chemical dilutions using the reference material formazan. Jackson turbidity units are historically based on sighting a flame through a volume of water. But all of these units are roughly comparable to each other, so you don't need to worry too much about which type of unit is being used. Turbidity in and of itself isn't a health risk. It depends on which particles are causing the turbidity. So there are no health-based targets around turbidity. However, turbidity can have significant impacts on treatment processes, including filtration and disinfection, so there are often operational guidelines before such treatment is applied, typically in the range of 5 to 10 turbidity units. This is also the range at which turbidity becomes noticeably visible, and people may have aesthetic concerns when they see that the drinking water is cloudy. Of course, when people are habituated to drinking turbid water, this may not pose any aesthetic problems. Perhaps the simplest form of HWTS is gravity settling or simple sedimentation. Here, you simply take a volume of water, set it aside, and let gravity do its work. Depending on the size of the particles will then be removed by settling to the bottom. This process can remove some turbidity and can improve the visual appearance, but has a very limited effect on pathogen removal, though some of the very larger pathogens, protozoa, helminth, eggs, can be removed. Also, when the water is being stored for sedimentation to occur, there's the possibility of introducing secondary contamination if the storage container is not hygienic. An example of simple gravity settling is the 3-pot sedimentation method. In this method, 3 different storage vessels are used so that drinking water has always been stored for at least 2 days, which gives time for some pathogens, such as schistosomes, the cause of schistosomiasis, to die off. So in this example, one always takes drinking water from pot number 3, and when it's empty, you can slowly pour water from pot 2 into pot 3, leaving the bottom sediments untouched, and then wash out pot 2. Then pot 2 can be refilled by slowly pouring water from pot 1 into pot 2 and washing out pot 1. Finally, you can pour water collected from the source, from a bucket, number 4, into pot 1, and if it's very turbid, you could strain this through a clean cloth. It's also possible to use a flexible pipe to siphon water from one pot to another without disturbing the sediments at the bottom of the container. Gravity settling has only limited reduction of turbidity, especially when the particles forming turbidity are small. But settling can be enhanced through the use of chemicals called coagulants. And what coagulants do is they make the particles in water stick to each other better. They also add new particles so that there are more particles around that can bump into each other, collide, stick, and form larger particles that are easier to settle out of solution. Many small particles suspended in water, like colloids, have a negative charge on them, and two negatively charged objects will repel each other, so they can't stick to each other. Coagulants add positive charges to this mixture. So the positive charge of a coagulant can neutralize the negative charge of a particle, or in some cases, a larger coagulant molecule can bridge between two negatively charged particles, helping them come together and settle out of solution. Coagulants can also remove some dissolved compounds and improve the color of the raw water. It's possible to make coagulants from locally grown plants. One of the most commonly used plants for this purpose is Moringa oleifera, shown over here on the left, which is grown widely in Africa and Asia. It's called the drumstick tree in Asia because of those long seed pods. To use moringa, you collect and dry the seeds and grind them into a powder, and then add them to water to be treated, often at a dose of about 200 milligrams per liter. There are many other plants that are used as coagulants. The prickly pear cactus is commonly used in Latin America, and nirmali seeds in India, which aren't very effective as a primary coagulant, but can help if another coagulant is present. And there are other plants available in different settings that are also used as coagulants. The way that these plant-based coagulants work is that the plant material contains a compound, a chemical, it's often a water-soluble protein, that has a positive charge. And in fact, it might have many positive charges and be polycationic. And that can interact with particles that have a negative charge to make them stickier and make them settle from solution. Plant-based coagulants tend to be most effective at higher turbidity when there are more particles around to bump into and stick to each other. So if the turbidity is at least 30 or 50, these coagulants will work better. Some of the plant-based coagulants, such as moringa, may also have some antibacterial properties as well, but in general they're not considered a complete treatment, but a precursor to be followed by a disinfection step. One disadvantage of the plant-based coagulants is that they add a lot of dissolved organic carbon to the water, which can foster regrowth of bacteria and eventually could cause taste and odor problems. Chemical coagulants are much more widely used than plant-based coagulants, and the most common of these are metal salts using aluminium or ferric iron. Aluminium sulfate, in particular, is widely available locally because it has many household uses. One of them is that you can use alum when shaving. If you cut yourself shaving and rub a little bit of alum on it, it stops the bleeding. So alum may be locally available. Alum consists of aluminium and sulfate and a number of water molecules, and the way that it works is it creates this aluminium ion with 3 positive charges, which are very able to interact with those negatively charged particles and help them to precipitate. Alum potash, using potassium as well as aluminum, is another locally available chemical coagulant. Ferric salts work well as well. They tend to be a little bit less widely available. They work well over a broader pH range than aluminium. Chemical coagulants tend to produce coarser flocks compared to plant-based coagulants, which means that they settle faster, but it also means that they create a larger volume of sludge. Let's take a look at a short video that demonstrates coagulation and flocculation. This video uses a product called the P&G Purifier of Water, produced by Procter & Gamble. It's the HWTS product formerly known as Pure, and it uses a combination of coagulation with ferric salts and disinfection with chlorine. Let's take a look. And stirring it rapidly to dissolve the salt and allow it to hydrolyze and create flocks and bump into the particles in the water. Then there's a period of slower settling and bumping when the particles get larger and larger and finally form flocks that settle to the bottom. The solution is then filtered through some cloth and stored for a while for the chlorine to be effective before the water is safe to drink. Coagulation is a complex physical and chemical process and can be affected by very many different operational parameters. The temperature is important. It doesn't work as well at low temperatures. And especially the characteristics of the water. The pH and the alkalinity are important variables. If the alkalinity is low, well, coagulation consumes alkalinity, so the pH can drop to very acidic levels if there's insufficient alkalinity. In that case, it might be necessary to add some lime or sodium carbonate to increase alkalinity. But if the alkalinity is too high, the pH is often high as well, and chlorination would be less effective. Another important factor is the physical mixing. It's important to mix rapidly at the beginning so that the coagulant dissolves and is spread evenly throughout the mixture and has a chance to bump into and interact with a lot of particles. Then finally, the dose should be optimized. If there's too much coagulant as well as too little coagulant, it doesn't work optimally. So the best practice would be to do a series of tests called jar tests with the actual water to be treated to determine the optimal dose. One issue that may arise in connection with coagulation where aluminium salts are used is that of residual aluminium in drinking water. Some studies have found a link between aluminium exposure and neurological problems, including Alzheimer's disease. However, other studies have not found these links. The World Health Organization has reviewed the literature, especially focusing on exposure through drinking water, and so far has decided not to set a health-based guideline for drinking water, in part because drinking water constitutes only a small portion of the total intake of aluminium, with food being a much larger factor. However, WHO does recommend for aesthetic reasons that residual aluminium be kept to certain levels in finished water because it impacts the visual appearance of the water. And in a large, well-managed system, it's easy enough to keep residual aluminium below 0.1 milligrams per liter, and in smaller systems below 0.2 milligrams per liter, through a combination of dose optimization and following coagulation with a filtration step. If you'd like to see the WHO's rationale for not setting a health-based guideline in more detail, take a look at the text from the WHO guideline values. So in summary, sedimentation is a pre-treatment step which is often necessary before moving on to filtration, disinfection, and safe storage. The purpose of sedimentation is to remove suspended solids, and this can be done either through gravity settling or through use of coagulants, either plant-based coagulants or salts such as aluminium or ferric salts. Sedimentation does result in some pathogen removal, but should not be considered as a complete treatment. However, it does allow subsequent treatment steps to be more effective.